Gas pressure is caused by the force and number of collisions of gas particles with the walls of the container. Some properties of gases. First, they compress easily. They compress easily because gas particles are spread throughout a container. So because they're so spread out, they can compress easily or be pushed together. They mix completely with other gases. So whatever room you're in, you have oxygen, you have CO2, you have nitrogen gas, to name a few, and all those gases are spread evenly throughout the room. They exert pressure on their surroundings, and they take the shape and volume of the container they're in. So these are the four that you should be writing under properties of gases. Pause the video until you're done writing them down. Temperature in the gas law unit needs to be in a new unit, which is Kelvin. So we have Celsius, we have degrees Fahrenheit, and we also have Kelvin. Kelvin was a temperature scale that's based on the lowest temperature possible, which is absolute zero. Absolute zero is 0 Kelvin. It's the temperature at which all motion would stop. So our equation to convert Celsius to Kelvin is you just add 273. If you have Kelvin and you're trying to get to Celsius, you're going to subtract 273. On your formula chart, it says 0 degrees Celsius is equal to 273 Kelvin. Kelvin cannot be a negative temperature. That's why that temperature scale was created. So nothing in the gas law unit can we have negative pressure, we can't have negative volume, and so that's why we need a positive temperature scale. So we can have negative Celsius though. So here we have negative 167 degrees Celsius. I'm going to add 273 to convert it to Kelvin. Make sure you're using the negative sign and not the subtraction sign. And that gives us 106 Kelvin. There's no degree sign for Kelvin, it's just a capital K. Below, if we're trying to go from Kelvin to Celsius, I'm going to subtract 273. And that'll give me 48 degrees Celsius. So we're just adding and subtracting when converting temperature. You won't multiply or divide. Go ahead and pause those next two. Restart when you're done. So you should have got in 1373 Kelvin. And negative 195 degrees Celsius. Make sure that you're showing work for those temperature conversions. Besides temperature conversions, we also are going to have pressure conversions. Pressure is a force applied over a given area. We measure pressure using a barometer. Barometers work by atmospheric pressure pushing down on this glass plate and then the mercury going up this column. That's how we get millimeters of mercury. So on your formula chart, 1 atm is equal to 760 mmHg, which is equal to 760 torr, which is equal to 101.3 kPa. So all four of those are pressure units. So just like temperature could be in Celsius, Fahrenheit, or Kelvin, pressure can be in atmospheres, millimeters of mercury, torr, or kPa, to name just a few. So we're going to start with the number that's given, with the unit, and just like we've done before, we're going to set up a chart. Whatever unit is here has to go in the bottom right, and I'm converting to kPa. According to our conversions a second ago, we have a 1 with atm and a 101.3 with kPa. My atm will cancel. Just like before, we're multiplying numbers on top, dividing the bottom. So we get 157.015. So 157 kPa. For this next one, I have 1300 torr. So torr will go on bottom, mmHg on top. And there's 760 mmHg for 760 torr. Since mmHg and torr are equivalent to each other, 1300 torr will be equivalent to 1300 mmHg, or millimeters of mercury. Go ahead and pause the video and do these next two on your own. Restart when you're done to check yourself. So you should have got in 1013 mmHg and 1.12 atm. STP we saw when we were doing the mole unit. 1 mole is equal to 22.4 liters at STP. STP stands for standard temperature and pressure. So if in a problem you're given STP, they're giving you a temperature and a pressure. You can also be given just standard temperature or just standard pressure. On your formula chart, standard temperature is 0 degrees Celsius and standard pressure is 1 atm. But remember that 0 degrees Celsius is equal to 273 Kelvin, and 1 atm is equivalent to all those other pressures. Kinetic molecular theory, or KMT, has 4 parts. The first part says the volume of individual gas particles can be assumed to be 0. Because in our container, the gas particles are so spread out and so small in comparison to the container volume that we can assume the volume of the gas particles to be 0. The particles are also in constant motion, and their collisions with the walls of the container are what cause pressure. The gas particles are not attracted or repelled by each other because they're so spread out and they're moving so rapidly that they don't have time to form attractions. When they do collide, their collisions are perfectly elastic, meaning all of their kinetic energy is transferred from one particle to another without loss. And finally, the average kinetic energy is energy of motion, so the average kinetic energy of a gas is directly proportional to the Kelvin temperature. In other words, when you increase the temperature, the particles are going to move faster. If you decrease the temperature, the particles are going to move slower. The last part is Dalton's law of partial pressures. Dalton's law states that the total pressure of a mixture of gases is simply the sum of the individual pressures of each of these gases, known as partial pressures. So the total pressure, so P total, which we'll represent with PT, is equal to P1 plus P2 plus P3 plus however many gases we have. So air is made up of oxygen, nitrogen, argon, water, CO2, and if we add up all of those partial pressures, we get atmospheric pressure. So in this problem, it's talking about total pressure and that we have 4 gases, and we're trying to find the pressure of the 4th gas. So we have PT is equal to P1 plus P2 plus P3 plus P4. Since I'm trying to solve for the pressure of the 4th gas, I can rearrange and say P4 is equal to PT minus P1, because I need to get P1 over to this side, minus P2, because I also need to get that one over, minus P3. Because when I get rid of 1, 2, and 3, then I'm going to be left with P4. The hardest part of Dalton's law is making sure that all of your units are the same. In this problem, we have ATM, ATM, and ATM. And we want our answer in ATM. So we can just plug everything in. So the pressure of the fourth gas is equal to our total pressure, which is 4.8 ATM, minus the pressure of the first gas, which is 1.2 ATM, minus the pressure of the second gas, which is 0.49 ATM, minus the pressure of the third gas, which is 0.78 ATM. So to solve, we just need to subtract them. So I got 2.33 ATM. For this last one, it says that we have 3 gases and they're talking about total pressure. So my total pressure is equal to the pressure of oxygen, because we have oxygen, plus the pressure of xenon, plus the pressure of helium. So we're going to replace the 1, 2, and 3 with the actual symbols of the gases if they tell us what gases that we have. Because then when it says that we're trying to find the pressure of xenon, rearranging becomes easier because we can say, okay, well, we have pressure of xenon. And so to solve for pressure of xenon, it's going to be the total pressure minus the pressure of oxygen minus the pressure of helium. If we look at it though, we have torr, kPa, torr, and we want our answer in torr. So this one is not in the right unit. So the first thing you need to do is convert your 74.1 kPa to torr, just like we did a few minutes ago. Once you get that answer, then that was our pressure of oxygen. So that's going to go right here. And then you can solve for the pressure of xenon. So go ahead and pause the video and try solving for your pressure of oxygen and then your pressure of xenon. Restart when you finish or if you get stuck. So my pressure of oxygen was 556 torr. And so to find my pressure of xenon, my total pressure was 972 torr minus what I just solved for, 556 torr, minus 348 torr. So we get 68 torr as our final answer.